Right, so last week we went this way, right? If I saw a plus b or a minus b squared, right, we could then recognize, oh, that's going to fall into this pattern, a squared plus or minus 2ab plus b squared, right? And in the same way, if we saw this pattern, a plus b times a minus b, we know that it would result in a difference of squares, a squared minus b squared, right? So today, because we're factoring, right, which means we're going the other way, right? We're looking at trinomials in this form and recognizing, oh, this is a perfect square, a plus b or a minus b squared, right? And in the same way, if we notice two perfect squares being subtracted or a difference of squares, we know that they can factor in the form a plus b, a minus b, okay? And so let's look at a couple examples. I want you to identify whether or not each polynomial is a perfect square, and if so, I want you to give its factored form, okay? So the key here is to identify, and we identify them by figuring out if they fall into this format, a squared plus 2ab plus b squared, okay? And so when we look at this x squared plus 18x plus 81, we're checking, hey, does this correspond to this, a squared plus 2ab plus b squared, okay? And we know it's the plus because we see the plus here, right? And so if we can identify a and b, then we can say, hey, I know that this is going to factor to a squared plus b squared, okay? And so the first thing we check for is the perfect squares themselves, right? And so I'm looking here, do I have a perfect squared? Yes, x squared is a perfect square. 81 is also a perfect square, right? And so we know that x squared and a squared, that means a is equal to x, right? This is x squared, right? Now, if I look here and I see an 81, then I know that corresponds to my b squared. Then b must be equal to 9, right? And so just having the a squared and the b squared, though, doesn't guarantee that it's a perfect square trinomial, right? This middle term has to match that 2ab. It has to be equal to 2ab, okay? And so we're looking, hey, does this equal 2 times a, which is x, times b, which is 19? And it does, right? 2 times x times 9 is going to give us 18x. And so I know for a fact that my answer here is a plus b, or x plus 9 squared, okay? But that's because it checks out, right? All the pieces check out, okay? So let's look at b. Is x squared minus 24x minus 144 a special product? Okay, so if we look here, we see x squared and we see 144, which are both perfect squares, but this is actually not a perfect square, okay? And the reason is because of this negative right here, okay? This last term cannot be negative, right? Notice it's always a plus, regardless of a plus b or a minus b, right? It should always be a plus because any number squared is positive. So if I have a subtraction sign right here, then I automatically know that it's not a perfect square, okay? Okay. And that's because we want it to look like this, right? A squared plus 2ab, or sorry, minus 2ab plus b squared. We need that plus there, okay? So let's look at this one. 4x squared minus 12xy plus 9y squared, okay? So if I look at just the way this is laid out, because we have the minus sign, we know we're looking at a squared minus 2ab plus b squared. And that factors to a minus b squared. And so, do I have two perfect squares? Yes. 4x squared, 9y squared, both perfect squares, right? This means that a is equal to 2x and b is equal to 3y, right? So then we have to check, hey, does 2ab equal 12xy? Well, 2ab is 2 times 2x times 3y, which is going to give us 12xy, right? And so because these match up, right, that minus 2ab, we know that it's a perfect square, and so it factors to 2x minus 3y squared. Okay, let's look at this one. a squared plus b squared, or a squared plus 2ab plus b squared. So we have two perfect squares, 16x squared and 25. So this is 4x squared, right? This is 5 squared, okay? So we're checking for that 2ab, right? Well, let's see. 2 times 4 is 8. 8 times 5 is 40. So this is 40x, but do we have 40x here? No. So this is no. This is not a perfect square because the middle terms don't match. Okay, the 20x is not equal to 2ab. Alrighty, so let's look at a couple more examples. Okay, we're going to factor each of these completely. Okay, and I'm going to come back to this, or I'm going to say this over and over, but we always check for a GCF first, no matter what. So let's look here. 3x squared minus 18x plus 27, right? Neither of these are perfect squares, but we need to check for a GCF. Do we have a GCF here? Yes, my GCF is 3, right? So I can factor out the 3, and I get x squared minus 6x plus 9. And that just so happens to give us a perfect square trinomial, right? A squared minus 2ab plus b squared, right? And we know that that's x squared, and that's 3 squared, right? So that means this needs to be minus 2 times x times 3, which checks out. And so we know that this is 3 times x minus 3 squared. We get that x minus 3 squared from that perfect square triangle, okay? So we factored out GCF and then saw the perfect square. And so this is our completely factored answer, okay? Let's look here. So because it's a binomial, we know for a fact that it can't be a perfect square. But what is a binomial? A difference of squares, right? So do we have a squared minus b squared? I have the minus sign. Do I have two perfect squares? Yes, 25a squared and 64 are both perfect squares. That means I know that this is going to factor to a plus b, a minus b. So in this case, this is going to become 5a plus 8 times 5a minus 8. And that is my answer. Okay. So, next one. 2x squared y plus 20xy plus 32y. Let's check for a GCF. All of them are divisible by 2, and they each have a y. So I could factor out a 2y. That leaves me with x squared plus 10x plus 16, okay? Which seems like a perfect squared trinomial, right? Because we have x squared and 16. But that means a is x and b is equal to 4, right? So 2ab in this case would need to be 4 times 2, which is 8, but our middle term is 10. So this is not a perfect squared trinomial, okay? But that doesn't necessarily mean it can't be factored, okay? Not a perfect square. Because we learned also last week that when we have an x squared, right? And that means we're really, to factor this, we're checking, hey, we want two numbers that multiply to 16 and add up to what? 10, right? Remember the product sum? We want a product of 16 and a sum of 10. So although it's not a perfect square, there is a way to factor it, right? We can say x plus 2, and then x plus 8, because 16 times 2, or 8 times 2 is 16, 8 plus 2 is 10. So this is the completely factored form. 2y times x plus 2 times x plus 8. So even though we don't have a perfect square, then we then kind of fall back on what we learned last week with the product sum rule, okay? So let's look here, let's check for a GCF. We have a GCF of x minus 1. And so if I factor out an x minus 1, that's going to leave me with a 16x squared minus 81. And so do we have a special product? Yes, we have two perfect squares that are being subtracted, so this is a difference of squares, right? So a difference of squares can then be split up further into a plus b, a minus b, or in this case, 4x plus 9, 4x minus 9, and we still have the x minus 1 from before. So my final answer is x minus 1 times 4x plus 9, 4x minus 9, okay? And so when we're asked to completely factor something, we have to consider all things, right? We start with GCF and just kind of go through that process of breaking things up, okay? Maybe this visual might help. Think about our factor trees, right? Whenever we did prime factorization, paste image, there we go, right? Think about breaking this up into factors, right? We identified the two factors here are if I take out an x minus 1, I'm left with a 16x squared minus 81, right? But we're not done factoring until we take every number that can be broken up. So this difference of squares is 4x plus 9 times 4x minus 9. And these can't be broken up any further, so my final factored form is x minus 1 times 4x plus 9, 4x minus 9. All right.